So we want to take a look at an example on how to use the inverse function theorem. We have the function f of x equals x cubed plus 2x plus 3, and I want to find f inverse, the derivative of f inverse evaluated at 0. So now you just need to have a map, okay? I have x comma y is on f, so y comma x is on f inverse. So if I want to find f inverse, the derivative of f inverse at 0, what I have right here is y equals 0. So I need to find my x. Okay, so my step 1, I need to find x comma 0 on f. I need to know what point I'm referring to, okay? Because once I know the y, right? So y, right here, I need to find the x that correspond to it. So what you will need to do is set up this equation, x cubed plus 2x plus 3 equals 0, and solve for it. Now most of the time we cannot solve for a polynomial greater than quadratic, right? Greater than second degree. Usually you won't be able to solve for x. That's true in the real life. And that's why the inverse function theorem is so powerful. You do not need to know the expression of f inverse. So in this case, we have no expression of f inverse, but it's okay. We don't need the expression. All we need is derivative at a point. So in that case, we need to find that x. And how do we find that x? We need to go back to what we learned from college algebra. We need to factor in order to solve for anything. Because anything greater than second degree, you do not have quadratic formula anymore. There's no formula. So the only thing you can have is factoring. So how do we factor? Well, it's an experience. You need to have some experience in factoring. When I see x cubed, I need another cube. So I can use sum of cube formula, okay? Because those are the few formula I have in hand. So I'm gonna break 3 into 1 plus 2. That's my I just have to try it, whether it work or not. Probably it will work, but if it doesn't work, I will think about another way. So I'm gonna break 3 into 1 and 2, right? Now if I break it in 2, I can see right away here 2x plus 2. So here 2x plus 2, I have a common factor of 2. X cubed plus 1 is the same as x cubed plus 1 cubed. I will just try the sum of cube formula. Okay, so I have x plus 1, x squared minus x plus 1. The second one, I factor out the 2, I get x plus 1 equals 0. Okay, now I look at this again, see what I have. I have a common factor of x plus 1. So I do x plus 1, and then for the rest, it's just x squared minus x plus 1 plus 2, so plus 3 equals 0. Now I can know already from the quadratic formula, this piece, I don't have a real root, okay? My delta is less than 0. So in that case, I can only have x plus 1 equals 0, and my x must be negative 1. Okay, so I find my x is negative 1. So the point negative 1 comma 0 is on the graph of f. So the point 0 comma negative 1 is on the graph of f inverse. And again, I want to verify. I plug in -1 back into f, and I want to make sure I get 0. Then I move on, okay? So now, I'm ready to apply the formula. So step 2, I just apply the formula. I want f inverse, okay, the derivative, evaluate at y, and my y is 0. Okay, so I'm referring back to this formula right here. G is the same as f inverse. Okay, it's just denoting the inverse of f. My y is 0. So then I have 1 over f prime of, now this number, x, what is x? I solve for it, it's -1. Okay, so now all I need to do is find f prime at -1. So what is my f prime of x? Okay, it's a polynomial, so it's 3x squared plus 2. Then I know what is my f prime of -1. I plug in -1, I get 3 plus 2, which is 5. So I just plug it back in here. I get 1 over 5. And that is what I'm looking for. Okay, derivative of f inverse evaluated at 0 equals 1 over 5.